Alright, welcome back everybody, and today we're going to be evaluating this very spicy looking integral right here, the integral from 0 to infinity of the sine of x to the n over x to the n, where our n is greater than or equal to 1. So this integral looks very familiar to the Dirichlet integral, and that's the case where n is equal to 1, so we just have sine of x over x in the integrand. But now we're going to be bumping it up one level. We're going to be taking a look at what if we have x to the n instead. So this is going to be a lot harder than our Dirichlet integral. So we're going to be using some complex analysis and differentiation on the integral sign to help us out right here, because this integral is in fact very difficult to solve using purely complex analysis. I've tried a number of different ways and nothing just works out nicely. So in order to get started right here, we're going to be first of all defining a new function f of t, and this function f of t is basically just going to be a parametrized version of this integral, and we're going to be using Leibniz rule for differentiation under the integral sign in order to kind of simplify this integrand a little bit. So this f of t, it's going to be almost the same thing. It's going to be the integral from 0 to infinity of the sine of, now we're going to place a new parameter t inside of this sign, so we have t times x to the n over x to the n dx. Okay, and now what do we want to do with this? We want to differentiate this function f of t, and the reason why we're doing all of this stuff is to get rid of this x to the n on the denominator using what we have inside of this sign right here. So if we differentiate this function with respect to t, that's going to be f prime of t on the left hand side, and on the right hand side we're going to have the derivative of this integral. Remember, this integral is actually in terms of t, because we have x as our variable, and that's just going to disappear in the integration process, leaving us with some kind of function with respect to t. So we're going to differentiate this integral with respect to t, and using Leibniz rule for diffing under the integral sign, we're going to bring the differential operator inside of the integral and have a partial derivative in there. So now we're going to have the integral from 0 to infinity of the partial derivative with respect to t of the sine of t times x to the n over x to the n dx. And well, notice that x to the n is just a constant in terms of t, so that can just come outside of the differential operator. So now we have the integral from 0 to infinity 1 over x to the n, partial derivative of a sine of t times x to the n with respect to t. That's nothing too hard to deal with because t is our variable, x to the n is our constant multiple of t. So if we just use some chain rule, first of all we have the derivative of the outside function, so that's just going to be cosine of t times x to the n, and we're going to multiply it by the derivative of the inside, which just happens to be x to the n. So we have x to the n like so, dx. Okay, and now you can clearly see that this x to the n on the denominator will actually disappear off. So now we're just left with f prime of t is equal to the integral from 0 to infinity of cosine of t times x to the n dx. And in fact, this integral is a lot nicer to evaluate using complex analysis than what we had at the very start. So this integral is what we're going to be focusing on now. And I guess I should mention one more thing, because notice this integral f of t, is not the same thing as what we had at the beginning, which we called I. So I'm calling this integral I, just so we know what we're solving later on. And what is the relationship between f of t and I? Well, the only difference is this t inside of this sign, and in fact, if you plug 1 inside of this function f of t, so f of 1, that's going to give you I back, because this t is going to turn into a 1, leaving us with this what we have at the very start. So we have this expression for f prime of t now, and what I want to do is I'm going to start kind of transferring everything into the complex plane. First of all, notice we have the cosine right here, and if you have the cosine of, let's say, some angle theta, then that's exactly the real part of e to the I theta, like so. So what I'm going to do, here we have cosine of some junk. I'm going to replace that with the real part of e to the I times that junk. So this integral is in fact still equal to the integral from 0 to infinity of the real part of e to the I times this junk right here, so t times x to the n. And you can verify for this yourself, because if you use Euler's formula, you're going to get cosine of this junk right here plus I times the sine of that junk. And if you take the real part, you're just going to get the cosine out the end. Alright, very nice. And now what I'm going to do is I'm going to interchange this real part operator and this integral. And the way that works is, notice that this inside right here, that's a complex number. We can write that in the form a plus bi. And if we're taking the real part of this, well, that's just going to be a, and then we're just integrating a, so that's what we're trying to do. But if we interchange these two operators right here, we're going to get the real part of the integral from 0 to infinity of e to the I t times x to the n dx. And what does that mean? Well, we're integrating both of these real and imaginary parts now. So this is the complex number. We're integrating both of the real and imaginary parts, and we can use the linearity of the integral to split it up, of course. And now if we take the real part of what we have at the end, well, that's just going to be this real thing we have at the end, because this is the imaginary part. It's still going to remain imaginary when we integrate it. So in fact, we can interchange those two operators. It's going to give us the same thing in the end anyways. Okay, and now what can we do? This is the integral that I want to focus on now, this very integral right here. And I'm going to call this integral j. And this is the integral where we're going to be starting to use some contour integration on. So with this integral, what is our integral j? Our integral j is equal to the integral from 0 to infinity of e to the I times t times x to the n and dx. So with this integral, what I want to do is I'm going to try and turn it into some kind of integral of the form e to the minus omega to the n, where omega is just some variable. And the reason why I want to do that is because the integral of this thing from 0 to infinity is very easy to evaluate. All you need to do is do a bit of a substitution and you get your gamma function right away. So if we can somehow transform this integral into this form right here, so we want this integrand instead, we can get some kind of a gamma function out the other side, which would be quite nice. So how can we do that? We want a minus omega to the n in the exponent, and notice we already have an x to the n, but the annoying part is we have this I times t multiple out the front, and we want to get rid of that somehow. And the way I'm going to do that, let's first of all focus on this t. Notice that t is the exact same thing as t to the 1 over n to the nth power. And if we do that replacement right there, if we imagine this t as being what we have right here, we have something raised to the nth power, and x raised to the nth power. And whenever you have that, using some exponential properties, you can bring those two bases together and raise it to the same power. So what do we mean by that? You're going to get the integral from 0 to infinity of e to the I, and now we're going to have the t to the 1 over n times x to the nth power dx. And you can verify for yourself that this still makes sense, because if you distribute this n into here, you're going to get t, and then you still have that x to the n that we started off with. Alright, very nice. And remember, we wanted e to the minus omega to the n. We're missing a minus right here, so in order to get a minus, why not multiply minus in? So we have the integral from 0 to infinity e. Let's just chuck in a minus, but we can't just chuck in a minus. We have to put a minus somewhere else to cancel it out. So we're going to group it with the I right here. So I'm grouping this minus and the I together. And we still have our t to the 1 over n times x to the nth power dx. Okay, and now what I want to do is replace this minus I with its polar form, because polar form is a little bit nicer when you're working with the powers. So minus I, that's the exact same thing as e to the minus I pi over 2. And now we're very close to getting it into that e to the minus omega to the n form. We're going to do basically what we did to this t right here, to this complex number right here. We're going to take the nth root and raise it to the nth power. And in doing so, we get something raised to the nth power, which we can combine with what we have over here so far. So I'm just going to write it out right here. We're going to have the integral from 0 to infinity of e to the minus, so this minus stays as it is. We're going to be transforming this e to the minus I pi over 2. That's going to turn into e to the minus I pi over 2n raised to the nth power, and then we have t to the 1 over n times x to the n dx. And notice that's basically what we have over here, because if you multiply this exponent n into here, it's going to cancel out with this n on the denominator, which is what we have over here. And now we're going to combine those two powers together, so bring the two bases together. We're going to get now the integral from 0 to infinity, e to the minus, and then we're going to have e to the minus I pi over 2n times t to the 1 over n times x, all that raised to the nth power dx. Okay, so this is very nice right here, because notice we have e to the minus some junk raised to the nth power, and we can in fact substitute that junk for omega. So if we make a substitution now, if we let omega be equal to e to the minus I pi over 2n times t to the 1 over n times x. So our variable is x right here, not t, it's x. If we differentiate both sides, we're going to get d omega is equal to, well, we just have some kind of constant multiple of x, so d omega is e to the minus I pi over 2n t to the 1 over n dx. And now we want to isolate our dx, so let's just bring all of this stuff onto the other side, and we can do that quite easily by just flipping the sign in the exponent. So dx is equal to e to the I pi over 2n times t to the minus 1 over n d omega. Okay, so we have all of that information now, and one more thing I want to do. Instead of having the integral from 0 to infinity, I'm going to replace this with the integral from 0 to r, and just simply chuck the limit out on the outside. So we have the limit as r approaches infinity of the integral from 0 to r. That's the same thing as what we had on all these other integrals. So now we can plug in all of this information into our integral. So now we have the limit as r approaches infinity of the integral. We're going to worry about our bounds later on, but let's focus on what we have right here. We're going to have e to the minus. This whole thing, we said that was omega, so we just have omega to the nth power. And our dx, well, we said that was e to the I pi over 2n times t to the minus 1 over n d omega. Okay, and now let's see what we can do. We can bring all this constant stuff onto the outside. So let's do that. We're going to have e to the I pi over 2n times t to the minus 1 over n, limit as r approaches infinity. Also, I forgot about the bounds. Let's figure out what the bounds are first of all. So if we plug 0 into this x right here, well, that's just going to kill off everything, so omega starts from 0. But if we plug r into this x right here, we in fact get this junk times r. So that's quite interesting. We're going to have e to the minus I pi over 2n times t to the 1 over n times r. So that's a bit of an ugly upper bounds, but it is what it is. So now, yes, we have this limit, and now we have the integral from 0 to e to the minus I pi over 2n times t to the 1 over n times r, e to the minus omega to the n d omega. Okay, so this is looking incredibly ugly, and you see the reason why we didn't just leave this upper bounds as infinity is because when we plug infinity into here, in fact we want it so it's some kind of complex number, because that's what it should be. Alright, so where can we go from here? Well, let's replace omega with z, because it's just some kinds of variable. We're going to be jumping into the complex plane right now. So let's replace it with z, And we want this upper bound to just be infinity in the variance. We don't want it to be pointing out in some random direction in the complex plane. We want it to be just purely, really infinity. And we're going to be using some contour integration to prove that this integral is the same thing as the integral from 0 to infinity. So how can we do that? We're going to be taking a look at what this path looks like in the complex plane. So if we draw up our complex plane, like so, notice that this complex number, we have e to the minus I pi over 2n. We have this minus right here, which indicates that our path is in fact pointing downwards, like so. So we're going from 0 to whatever this number is. And I also want you to notice one small detail right here. As r approaches infinity, it really doesn't matter what this t to the 1 over n is, because we're assuming that's always positive. So in fact, we can just get rid of this t to the 1 over n, because in the limit as r approaches infinity, everything's going to go to infinity here anyway. So this is just r. So this is the path we're actually integrating on right now. It's a bit of a weird path that's pointing down in the complex plane, but it's what we have. And we want to show that this path is in fact the same path on the real axis. So from 0 to some big number r. And these two paths are in fact equivalent as our r approaches infinity. And the way we're going to just prove that is by using contour integration. So how can we make a bit of a contour out of this? Well, it's quite easy. We just construct some kind of arc right here. And that arc we're going to call it gamma. And this path that's going down, we're going to call it psi, okay? And we can write out a couple of integrals with this, because notice the integral along psi. So if we go down this way, and if we add the integral going in the positive direction on the gamma, and if we add the integral going from r back to 0, what this going to give you is actually 0, because this is a contour that closes a completely analytic domain, because the exponential function is entire, and we just have z to the n right here, negative z to the n, and that doesn't have anywhere that blows up or anything. So this whole function is entire everywhere, which means that if we make a loop in the complex plane, the integral over that loop, that contour, is 0, and that's Cauchy's integral theorem. So this whole thing is equal to 0. And what we can do right here, we can chuck this integral onto the other side. That's going to give us the integral over psi plus the integral over gamma is minus the integral from r to 0, but we can use that minus to flip the up and lower bound, so reorientate it. So we can reorientate it a little bit, so we have the integral from 0 to r. And that's the integral that we want, because when we take the limit as our r approaches infinity, this r just becomes infinity. It's not some weird complex number. And to remember, the integral over psi is what we have. The integral from 0 to r is what we want, and all that's really left is this integral over gamma. This integral over gamma, what we want to show that this integral goes to 0 in the limit that r approaches infinity, because if this goes to 0, then what we can say is that in the limit as our r approaches infinity, the integral over psi, which is what we have right here, is really the same thing as the integral from 0 to r, which is what we want. So our goal now is to show that the integral over gamma goes to 0 in the limit. So let's rub out what we have right here. We don't need it anymore. So what we want to show now is that the integral over gamma goes to 0. So the integral over gamma of this very function right here, e to the minus z to the n dz. And all we can do, first of all, let's just take the absolute value of it. And we're going to be finding an upper bound for this thing. And before we do that, let's just parameterize this function. So this is equal to the absolute value of the integral. And we can kind of do this in our head just to save some time. The integral, it's going to be parameterized as a function of angle. So our angle is going from minus pi over 2n. So minus pi over 2n like so, all the way up to 0, because an angle of 0 is right here. And we have e to the minus, well, z, how can we parameterize z? Z is just r times e to the I theta but this whole thing raised to the nth power. So r times e to the I theta just gives us the set of points along this arc of radius gamma, and our theta is going from minus pi over 2n to 0, of course. And when you parameterize this dz right here, you get d theta, but you also get some kind of multiple out the front, and that's just the derivative of this parameterization right here, which is I times r times e to the I theta. Alright, and since we're dealing with the real variable right now, we can use the integral inequality to say that this is less than or equal to the integral of the absolute value, so integral from minus pi over 2n to 0 of the absolute value of whatever's inside right here. So absolute value e to the minus r times e to the I theta to the n. Absolute value of I is 1, absolute value of r, well r is just a big number, just a constant, so let's chuck it out the front. Absolute value of e to the I theta is 1, so we can just close off the absolute value there. And now from here, let's we should distribute the power as well, just to simplify things a little bit. So this is r to the n, and then e to the I theta n. Let's use some Euler's formula right here. So this is equal to now r times the integral from minus pi over 2n all the way up to 0 of the absolute value of e to the minus r to the n. First part of this, that's going to give us the cosine of theta n. And then we're also going to get the imaginary part, which happens to be minus r to the n, I times r to the n, a sine of theta n and d theta. And notice we have e to the something minus something else, and we can use exponential properties to split that exponential up. So we have e to the minus something and e to the minus something over here. And now we're taking absolute values of this thing, we can split it up a little bit. So this is equal to r times the integral from minus pi over 2n to 0. Absolute value of this first part in this product right here, well, that's just e to some real number, but e to some real number is just positive, so we can drop the absolute value. So we just have e to the minus r to the n cosine of theta n. And on the second part right here of this product, we have the absolute value of e to the I times some real number right here. And whenever you have that, the absolute value is just 1. So we can just ignore what we have over here. So theta n and d theta. And now we want to estimate this integral further, and we want to take a look at this function in here, e to the minus r to the n cosine of theta n. So we have e to the minus some real number, and this number is in fact always positive on this interval minus pi over 2n to 0. So here we're just dealing with a decaying exponential, and what does that look like? It looks, let's just draw a picture over here, it looks something like this. And one of the properties of this is that if you pick two values a and b, so if a is less than b, then e to the minus a is actually greater than e to the minus b. And of course we have this r to the n right here, that's just some scalar multiple, it doesn't really affect this relationship right here, as long as it remains positive. So this is what we have right now, and the way we're going to estimate this integral further is by kind of interpreting this integrand as e to the minus b, because if we can find some kinds of e to the minus a that's bigger than e to the minus b, which is what we're thinking about this integrand as, we can find a further upper bound for this integral. So the idea is, let's think about this integrand as e to the minus b. We want to find some kinds of e to the minus a so that this thing right here is an upper bound for what we have already. And to find this a value, we need a that's less than b. So if we let b be equal to this cosine right here, we want some kinds of a that's always less than this cosine. So what does this cosine function look like? It looks like, well, at least on this interval, it just looks like this. So if you can graph this out on Desmos if you want to, but we have the point 0, 1 right here, as well as the point minus pi over 2n, comma, 0. So that's our x-intercept kind of, or our theta-intercept, because we're on the theta axis. So how can we find some a that's always less than b? Well, remember, b is this cosine right here. We're interpreting the b right here as this cosine function. Let's say we let a be equal to just this straight line segment that kind of connects those two intercepts? Well, notice that a is always less than or equal to b. So this should be, in fact, less than or equal. It still works out that way. So if we just let a be equal to this line segment, and that line segment's pretty easy to find out. Notice that we just need to compute rise over on, which is 1 over pi over 2n, which is 2n over pi. So 2n over pi times theta. So that gives us a line with this gradient right here, and it intercepts at 1 on the y-axis, so we'll just add in 1. This is in fact the equation of the line that passes through those two intercepts, and it's always less than or equal to this cosine. And since it's always less than or equal to that cosine, if we replace this function with the cosine, then what actually happens is that our integrand has a new upper bound. So let's just do that. So this is now less than or equal to r times the integral from minus pi over 2n all the way up to 0 of e to the minus r to the n. And let's do that replacement right there. Remember, this line is kind of like a. So a is less than b. That means e to the minus a is greater than e to the minus b. So now we just have 2n over pi times theta plus 1, like so. And this integral, we can actually evaluate it. It's really not too hard to evaluate. So to evaluate this thing, let's just bring it up over here. This is going to be equal to, so long equal sign like so. So this is equal to r. Let's find an antiderivative of this thing. That shouldn't be too hard to do. It's just a bunch of reverse chain rule bunch of times. So you're still going to get that exponential function of e to the minus r to the n, 2n over pi times theta plus 1. But you also got to divide by whatever's multiplied into this theta right here. So we need to divide by 2n over pi right here. So it's 2n over pi. And then we also need to divide by this minus r to the n multiple. So we're going to also divide this by minus r to the n. And we want to evaluate this thing from minus pi over 2n all the way up to 0. So what happens if we do that? Let's kind of clean things up over here. Let's flip this pi up to the very top. And notice right here we can kind of combine those two r factors. So we're going to have 1 over r to the n minus 1 with the negative, and we might as well put a pi there and a 2n. And what we're going to have on the inside right here, if we plug 0 into this theta, we're going to have, well, just 1 inside of that bracket. So if we plug 0 in, we're going to have e to the minus r to the n. And if we plug minus pi over 2n into here, we're going, notice that this pi and this pi will cancel each other out. This 2n and this 2n will cancel each other out, leaving us with just a negative 1. But minus 1 plus 1, that's a 0. And, well, that's just going to kill off this whole exponent. So we're just left with e to the 0. And that's going to be 1. So what did we just show right here? We just showed, remember we always use the less than or equal to inequality. We just showed that the absolute value of this integral is less than or equal to this thing right here. And let's just, I guess we can just bring that minus inside of that bracket to get pi over 2n times r to the n minus 1 times 1 minus e to the minus r to the n. Okay, very nice. And remember, our goal is to show that the integral over gamma goes to 0 in the limit as our r approaches infinity. So if we take the limit on both sides, so the limit as r approaches infinity on the absolute value of the integral over gamma, notice that n is always greater than 1, which means that n minus 1 is greater than or equal to 0. And we also have this very strong decaying exponential right here. So as r gets bigger and bigger, it's going to vanish up to 0. So you can clearly see that this thing really goes to 0 in the very end. Alright, so we've just shown that our integral over gamma goes to 0, which means that this relationship right here holds. The integral over psi is the exact same thing as the integral from 0 to r. So let's pick up where we left off, which was right over here. We can say that this integral, this whole entire thing, that's now equal to e to the I times pi over 2n times t to the minus 1 over n times the limit as our r approaches infinity of the integral from 0 to r of e to the minus z to the n dz. So that's quite a bit of work just to show that we can get rid of this complex number right here. But now let's just plug in I equals infinity, and we're going to get the integral from 0 to infinity, e to the minus z to the n dz. And just like I said before, this is what we wanted because we can turn this into a gamma function quite easily. And the way we're going to do that is we're just going to introduce a new substitution. So let u be equal to z to the n, which means du is equal to n and z to the n minus 1 dz. Just some basic power rule right there. But notice we can split this up a little bit. So this is n times z to the n and z to the minus 1 dz. But the z to the n, that's exactly our u. So we have n times u, and we also have z to the minus 1 dz. And how can we get our z? Well, our z is exactly the nth root of u, so u to the 1 over n. So this is equal to n u to the 1 over n to the minus 1 dz. And this is n times u times u to the minus 1 over n dz. And this is equal to n times u to the 1 minus 1 over n dz. And remember this thing right here, that's our du. And we want to isolate our dz because we want to solve for our dz. So our dz, if we bring on everything onto the other side, that's exactly 1 over n u to the minus 1 u to the 1 over n. So just chucking a negative inside these exponents right here times du. And this is equal to 1 over n times u to the 1 over n minus 1 du. That's quite a bit of working out just to figure out one differential, but let's just plug everything in. So this is equal to now e to the I times pi, what did I? This should be an n, not a pi. So pi over 2n, t to the minus 1 over n, integral. And what are our upper and lower bounds? If we plug 0 into this z, we're going to get a 0. And if we plug infinity into the z, we're going to get an infinity. And then we're going to have e to the minus z to the n, that's our u. And what does our dz becomes? It becomes 1 over n. And then u to the 1 over n minus 1 du. Alright, we can rub out all of this now because we don't need it anymore. So now this looks basically like our gamma function. Let's just rewrite it a little bit. Let's bring this 1 over n multiple out to the front. So we're going to have 1 over n times e to the I pi over 2n times a t to the minus 1 over n integral from 0 to infinity of u to the 1 over n minus 1 e to the minus u du. And notice we have u to something minus 1, and this in fact is gamma of that something, so gamma of 1 over n, like so. So let's do that replacement on our integral. We have 1 over n times e to the I pi over 2n times t to the minus 1 over n times gamma function of 1 over n. Alright, so we've done quite a bit of work so far. Remember, what exactly is this? This is our j that we had right here. And now let's take the real part of j. What is the real part of this thing? So real part of j, this is not too bad to evaluate because the only imaginary thing is this e to the I pi over 2n. And we can easily figure out its real part just by taking the cosine of this argument. So this is equal to 1 over n cosine of pi over 2n of t to the 1 over minus 1 over n times the gamma function of 1 over n. Alright, and remember the real part of j, that's exactly f prime of t. So this thing right here is exactly f prime of t. Okay, so we've figured out f prime of t, and now we want to get back to our f of t, because f of t is how we can figure out the value of our I. So how do we get back to our f of t? We have our f prime of t, but we want our f of t. So in order to get back, all we have to do is integrate. So f of t is equal to the integral of all this stuff right here. But I'm going to just make one little replacement. I'm going to replace this t with another variable. Let's call it y, for example, and we'll see y later on. So this is equal to the integral of 1 over n cosine of pi over 2n, y to the minus 1 over n, and gamma of 1 over n, dy. And notice this stuff and this stuff, those are just constants, so let's chuck it outside the integral. Before I do that, let's just figure out the bounds of this integral. And you might be saying, well, why do we need bounds? We're just taking the antiderivative of this thing. The reason is because I want to figure out the initial conditions and everything all in one go. So if you have the integral of f of t, for example, dt, and you evaluate at some bounds a to x, well, that's exactly the primitive function, so f of x minus f of a. And a is kind of like the initial condition, and if we want our primitive f of x, then we just need to add on f of a onto the other side, and that's going to give us our primitive, and it takes into account the initial conditions all in one go. So that's basically what I'm trying to do right here. So what's our initial condition, kind of? Well, if you look back on our f of t right here, what happens if we plug in a 0, for example? So what's f of 0? Well, let's plug 0 into here. We're going to get 0 inside of this sign, which means that sine of 0 is 0, which means that this whole entire integrand is 0. So if we're integrating 0, that's a 0. So in fact, f of 0 is exactly 0. So this is kind of like our initial condition right here. If we start at 0 and we run our integral all the way up to t, which is the variable we want to deal with, if we do that, we also have to add on the initial value on the end, which is 0, but that doesn't really change anything. So all we have to do to find f of t is evaluate this integral, and that's quite easy to do. Let's first of all check out those constants. So 1 over n cosine of pi over 2n, and gamma of 1 over n, integral from 0 to t of y to the minus 1 over n dy. That's quite easy to integrate because this thing right here, that's just going to turn into y to the 1 minus 1 over n over 1 minus 1 over n. So we're just adding 1 to that power right there. And we're evaluating this from 0 to t. If we plug 0 into the y, then it's going to be 0, so we don't have to worry about that. And if we plug t in, well, we're just going to replace y with t. So nothing too crazy happens there. So what we should end up with is 1 over n cosine of pi over 2n, gamma of 1 over n, and this integral turns into, we're just replacing this y with a t, so we have t to the 1 minus 1 over n over 1 minus 1 over n, like so. Alright, and what did we just find? Remember, this is exactly our f of t. That's the f of t we wanted to find out. And we are very, very close to finding our original I, because remember, I is exactly f evaluated at 1. So let's plug 1 in. If we have f evaluated at 1, what do we get? Well, we're going to have right here 1 raised to some power, and 1 raised to some power is exactly 1. So, in fact, f of 1, remember that's our I, and that's equal to 1 over n cosine of pi over 2n, gamma of 1 over n, and then we're going to have 1 over 1 minus 1 over n. And the nice thing is, if we multiply this n into this denominator right here, we can cancel some stuff out. That's going to leave us with the final expression of cosine of pi over 2n times gamma of 1 over n, all divided by, and n times 1 is n times 1 over n is minus 1, so n minus 1, like so. And this right here, that's exactly f of 1. That's our final answer for today's integral. Let me just check my notes, make sure that that's actually the right answer. I don't want to mess this up. And yes, it is the correct answer. So that's quite a complicated expression right there. We've got a gamma function there and everything. But yeah, that's the solution to this kind of generalized Dirichlet integral. So you can plug in any value of n, and well, you get the value for that specific integral. And I guess one thing to mention is that this expression doesn't explicitly work for n equals 1, because notice if you plug 1 in, you're going to get a 0 on the denominator. So technically this should have been n is strictly greater than 1. Alright, so this is me from the future. Thankfully I haven't rubbed out this whiteboard yet because I didn't explain this part entirely correctly. But if you let n be equal to 1, you're going to get a 0 on the denominator. And if you let n equals to 1 in this cosine, you're going to get cosine of pi over 2, which is 1. And gamma right here, gamma of 1 over 1 is just 1, so nothing really happens there. But essentially what you have is a 0 divided by 0 situation right here. So let's just use some L'Hopital's. So if you differentiate the top and differentiate the bottom, you're going to get, first of all, the sine of pi over 2n, minus sign actually, and you also got to use some chain rule, so let's multiply that by pi over 2, and chain rule again because you have this 1 over n function on the inside, so derivative of 1 over n is minus 1 over n squared, and derivative of the bottom is just 1, so we can just leave that out. Now if you let n be equal to 1, so if you take the limit right there, sine of pi over 2, because this n is equal to 1, so sine of pi over 2 is 1, so you've got minus 1 times pi over 2 times, well, if you let n equals 1 right here, that's 1 over 1, which is just, well, minus 1. So times minus 1. These minuses cancel each other out, leaving us with pi over 2, which is the exact value of the Dirichlet integral. So in fact, if you take the limit on this thing as n approaches 1, you do get the same result as if n was actually equal to 1. And I graphed it on Desmos. In fact, you do get some kind of curve that looks like this. So this is the point 1 right here, which is undefined, and this kind of plateaus off to 1. So this graph, if this is the n-axis, it kind of asymptotes out to 1. This is a very bad graph, but yeah. One more interesting thing is that this thing actually continues below 1 and does some crazy stuff in here. I'm not sure like the actual domain of n for this thing, where this thing converges, because I've plugged in values of n like 0.6 and 0.55 into Wolfram Alpha, and all those values of n converge, but once you get to around like 0.5 or 0.52, I'm not quite sure, somewhere around there, then the integral actually diverges. So it's a little bit interesting. I'm not too sure as to which of values of n is kind of like the lowest limit for where this integral converges, but yeah, it's somewhere around there. But just to keep things simple, we're just going to say that n is greater than 1. So yeah, that's pretty much all for this video. I hope you guys enjoyed it, and up until the next video, have yourselves a wonderful day, and I'll see everyone later. Bye bye.